Welcome to another deep dive. Today, we're tackling a classic.
Oh, the big one.
Structure and Interpretation of Computer Programs, SICP, for those in the know.
Right.
It's an MIT legend,
Yeah.
known for its challenging take on programming. You all sent in some excerpts, so let's dig in and see what makes this book so special.
I think it goes beyond just coding. It really dives into the core of what computation is, how we think about solving problems.
It jumps right in, doesn't it? It says, programming languages, they're not just for telling computers what to do, they're powerful tools for expressing ideas and methodologies. Like, what's the deeper meaning there?
Well, imagine this.
Hmm,
When you're writing a program, you're building a model of the problem you want to solve, right?
right?
And the language you choose, it kind of shapes how you think about that problem, influences the solutions you come up with. And SICP, it goes deep into this, showing how different programming styles lead to different solutions.
You know, one of the excerpts even mentions quantum mechanics running on computers composed of. I mean, programs simulating the very fabric of reality. That's wild.
It really shows how powerful computation is.
Mhm.
We can model incredibly complex systems from the tiny, tiny subatomic level to like the entire cosmos.
Wow.
And this leads to another big theme, especially relevant today, managing complexity in these massive software systems we're building.
Yeah, as our software gets more complex, having the right tools and methods becomes even more important. Speaking of tools, SICP uses Lisp, specifically the Scheme dialect. Is that choice significant?
Oh, absolutely. Lisp, especially Scheme, is known for its powerful abstraction capabilities.
Yeah.
It lets you express those very ideas and methodologies we were talking about in a really elegant, concise way.
So the language itself is key to the creative process, like choosing the right tool for the job.
Exactly. Now, let's look at some specific examples of this abstraction from the excerpts you sent. The concept of syntactic sugar comes to mind.
Ah, yes. The infamous quote, syntactic sugar causes cancer of the semicolon. A bit dramatic, but definitely memorable.
There's a point there, though. Syntactic sugar refers to shortcuts in a language's syntax.
Okay.
At first glance, they might seem helpful,
Yeah.
but SICP argues that they can make the code harder to understand and maintain over time. It's all about clarity and simplicity
Oh.
over, superficial sweetness.
But isn't some syntactic sugar helpful in practice? I mean, where's the line between being concise and clear?
That's the challenge, right? It's a balancing act. SICP encourages you to think about the trade-offs. Lisp, with its minimal syntax, it really forces you to confront the core logic of your problem, leading to more robust and understandable solutions in the long run.
So it's all about picking the right level of abstraction for the task. And speaking of levels of abstraction, SICP digs into different ways Lisp can evaluate expressions, like applicative order and normal order.
Oh yeah, this is where things get really interesting, especially for anyone who's worked with infinite data structures or those tricky side effects. Applicative order evaluates arguments before applying a function,
Okay.
while normal order only evaluates them when needed. This difference can drastically change how a program behaves and its efficiency.
It seems like SICP isn't giving hard and fast rules, but more like showing you different ways to think about problems and choosing the best approach.
You got it. Now, you marked a few interesting examples in your notes. One that jumps out is order of growth,
Hmm.
which relates to the efficiency of algorithms, right?
Exactly. This seems super relevant for those of us dealing with huge data sets or applications where performance is critical.
SICP uses order of growth to compare how algorithm efficiency changes as the input size grows. It's like think of comparing a bicycle to a rocket ship. They're both transportation, but their effectiveness depends heavily on the distance, right?
So it's not just finding a solution, it's finding one that works well even as the problem gets bigger. What about the Fermat test for prime numbers? That one caught my eye too.
Ah, the Fermat test. This is where things get clever.
Mhm.
It uses modular arithmetic to quickly figure out if a number is likely prime. It's like a shortcut, so you don't have to check all possible divisors, which can take forever for big numbers.
So far, SICP seems like an exploration of problem solving from all these different angles. We haven't even touched on the concept of representing numbers as functions, the so-called church numerals.
That's a whole other layer of abstraction we'll get into next time. It might sound mind-boggling, but it beautifully shows the power of thinking about information as processes instead of static things.
Welcome back to our SICP deep dive. Last time we left off with that cliffhanger, those church numerals, ready to untangle numbers as functions.
Let's jump right in. Imagine the number 3, not as the numeral we see, but as a function that applies another function 3 times.
So instead of three apples, it's apply apple three times. Like numbers are actions, processes.
That's it. A core idea in Lambda calculus, the heart of functional programming.
Why go to such lengths, though? Why represent numbers this way? What's the benefit?
It might seem abstract, but church numerals show how we can build complex systems from simple pieces. It highlights abstraction, thinking about computation in terms of functions.
Like building with functions instead of blocks.
Exactly. And remember SICP's emphasis on managing complexity. Church numerals fit right in, offering elegant solutions in a seemingly limited framework.
This brings us to a key aspect from the excerpts, SICP's view of time and computation. We don't always think about that directly when coding.
True, most programming treats time as implicit. But SICP, it really focuses on how we model and handle time within our programs.
So how does SICP approach this time and computation?
It looks at various sides of it, like objects with state, where data changes over time. Then there's concurrent programming, multiple processes running at once, introducing the challenges of syncing them up and making them talk to each other.
Sounds complex. How does SICP help us navigate that?
It provides a way of thinking about time as a key player in our programs. We learn to design systems that behave as expected, even with concurrent actions and changing data.
One excerpt mentioned non-deterministic programming and lazy evaluation too. Do these tie into SICP's handling of time?
Absolutely. Non-deterministic programming accepts that some computations might have multiple outcomes, bringing in uncertainty. Lazy evaluation puts off calculations until their results are absolutely needed.
So it's about strategically managing when things happen in our code, which can be really important for efficiency, especially with big, complex systems.
Exactly. SICP gives us the mental tools to think about time not just as something external, but something we can model and work with directly in our programs.
This focus on elegant solutions isn't just theoretical. SICP's ideas have had real-world impact, haven't they? Like that example with calculating the solar system's motion.
Yes. Researchers used Lisp-based tools to make a breakthrough calculation of how the solar system moves. They were able to push past previous calculations by a huge amount.
It's amazing how these abstract concepts can lead to real results in fields like astrophysics. The acknowledgments in the book stood out to me too. It spends pages thanking tons of people and institutions.
That really shows how knowledge building in computer science is collaborative. SICP itself builds on the work of so many people, showing how ideas evolve over time.
It's a reminder that even a groundbreaking work like SICP is part of a larger conversation, a collective effort to push the limits of what we can do with computation. Welcome back to the final part of our SICP adventure. What a journey it's been exploring this legendary book.
It really has, yeah. We've gone from the philosophical foundations of programming to the very practical stuff, managing complexity.
And those church numerals, representing numbers as functions, it's still kind of mind-blowing.
The beauty of abstraction, right?
Yeah.
Stripping away the familiar can reveal deeper truths and more elegant solutions.
Last time, you left us with a great question. How can we apply SICP's lessons outside of just computer science? What systems or concepts in our lives could use a deep dive?
It's all about taking those mental tools we've been sharpening, the abstraction, the modularity, how to handle complexity, and applying them to different areas. Think about a system you encounter regularly, one that seems really complex.
Well, I've always been fascinated by how cities work. The constant flow of people, traffic, resources, information. It's a complex system that somehow keeps going.
Cities are a great example. Think of them as interconnected modules. Transportation, energy, communication, governance. Each one with its own complexities.
And the feedback loops, they're crazy. Like improving public transport could ease traffic, leading to cleaner air, which then might improve public health. It all connects.
You're already thinking about the city computationally, like inputs, outputs, feedback mechanisms. Finding the right abstractions is crucial for understanding those relationships.
It's like those levels of abstraction in SICP. You can zoom in on a specific neighborhood or zoom out to see how the city fits into the larger region. Each view gives you different insights.
Choosing the right lens to examine the system. Each magnification reveals new details and helps us build a better overall understanding.
SICP's lessons seem to apply almost everywhere. It's like training your brain to see the world as a web of systems and processes.
Exactly. And to see the power of breaking down that complexity into manageable pieces, remember, order of growth. It's not just for algorithms. It helps us understand how systems scale, what happens as things get really big.
So whether I'm building a website, writing a book, even planning a trip, SICP's ideas about modularity, abstraction, and efficiency can be so helpful.
You got it. It's a way of thinking, a toolkit for navigating complexity, no matter what you're doing. The process of learning from SICP is valuable in itself, even if you're not a programmer.
It's about expanding how we think and tackling the challenge of understanding complex systems.
And who knows what amazing discoveries we'll make along the way.
This has been a fantastic deep dive into SICP. Thank you so much for your expertise and taking us on this journey.
It's been my pleasure. Keep those brains working and happy exploring.
And to all our listeners, we hope you enjoyed this deep dive into SICP. Until next time, keep those minds curious.